particle moves along a line with an acceleration function a of t equals 3 plus cosine t. The initial velocity is negative 4 meters per second, and initial position is 10 meters. Find its position function. So we are given an acceleration function here, and we're asked to end up with a position function. So we're going to be working backwards. So we know we're going to be using the idea of computing an antiderivative. If we're working from acceleration, the antiderivative of acceleration will be velocity, and then the antiderivative of velocity will be position. So this is going to be an antiderivative problem. But before we figure out our antiderivatives, let's look at some of the information that's given to us. So it tells us here that the initial velocity is negative 4 meters per second. So what that means is at time 0, the velocity is negative 4. In other words, v of 0 is equal to negative 4 meters per second. So I like to go ahead and write this out mathematically as v of 0. In addition, the next piece of information says the initial position is 10 meters. So again, if I write that out mathematically, we're saying that the position, I'll use s for position, at time 0 is equal to 10 meters. So s of 0 is equal to 10. So we sometimes call this type of problem an initial condition problem because we've been given some initial conditions, and these are going to help us to determine an exact antiderivative rather than a general antiderivative. So let's take our acceleration function that we were given. Let's go ahead and compute the antiderivative. So this would be the general antiderivative of this function, which will be velocity. So the antiderivative of 3 will be 3 times t. The antiderivative of positive cosine t will be positive sine of t, plus some unknown constant. We'll just call it c. Now, just a reminder here, if you were wanting to check this, and sometimes I just would check it in my head, or perhaps you'll do a check off to the side, we would check this antiderivative by computing the derivative of this function. So the derivative of velocity, we know, is going to give us acceleration. The derivative of 3t is 3. The derivative of sine of t is cosine of t, and the derivative of a constant would be 0. So we're just verifying that we do indeed get the original acceleration function that we were given. And again, that's going to be a check that you probably are not going to actually write out on paper, but rather a check that you would just want to do in your head to be sure that your antiderivative is correct. So now we are going to be able to use the initial condition v of 0 equals negative 4 to help us solve for our constant. So that means that our velocity is negative 4 when our time is 0. So that would be a time where we're going to substitute in 0 for time. So negative 4 is equal to 3 times 0 plus the sine of 0 plus a constant. So once I have my substitution, then we can go ahead and solve for c. In this case, 3 times 0 is 0, and the sine of 0 is also 0. Therefore, we're going to end up with our constant value, which is negative 4. So now, rather than writing our general velocity function, we can write a specific velocity function. V of t equals 3t plus the sine of t, and then our constant we just found is a negative 4. So we'll have a minus 4 for a velocity function. So now, if we find the antiderivative, of velocity, then we will be working backwards to position. So this is going to be our general antiderivative right now. So I have the antiderivative of 3t, so we can just leave the coefficient in front. This is t to the first power, so we know we will add 1 to our exponent. That means we'll have a t squared, and then we will be multiplying by the reciprocal of t squared, which means we're really going to multiply by a 1/2. Then the antiderivative of sine of t, be careful here because we know it's going to be some version of cosine, but remember, The derivative of cosine would give us a negative sign. And we don't want negative sine of t, we want positive sine of t. So therefore we need to have a negative cosine t for the antiderivative. The antiderivative of negative 4 will be negative 4 times t. And then again, we need a constant. Now, I don't want you to put a plus c here because that would imply that this constant is the same as the original constant. And that is not necessarily going to be the case. So you have two options. You could use a subscript. You could call the original constant c sub 1 and then call this one c sub 2. However, I tend to not even want to bother with subscripts, so I just work down the alphabet and I call this constant d. So right now, my position function is going to be s of t equals 3 halves times t squared minus the cosine of t minus 4t plus some unknown constant, we'll call it d. And now we'll go ahead and use our initial position here. S of 0 is equal to 10 meters. And we'll substitute in that position at a time of 0. So our position is 10. So 10 is equal to 3 halves times 0 squared minus the cosine of 0 minus 4 times 0 plus that unknown constant, we'll call it d. So I'm substituting 0 in for time, and my initial position was 10 meters, and that will let us now solve for d. So just be careful here, because a lot of this is going to go away and become 0, but remember, cosine of 0 is actually equal to 1. So therefore, we have negative cosine of 0, which would be negative 1, plus d. So therefore, when I add 1 to both sides, my d value is actually 11 in this case. So if I substitute that constant back into my position function, I now have a very specific position function that satisfies these two initial conditions we were given. So s of t is equal to 3 halves t squared minus the cosine of t minus 4t plus 11. And this would be the specific position function given the initial velocity and the initial position that we were given.